Hello everybody and welcome to today's lesson on segment lengths in circles. Today's objective is we will be able to find the lengths of segments of chords, tangents, and secants. And in order to do that, we first have to review some vocabulary. In the last lesson, we learned some different names of segments and lines as they interact with a circle. So let's start by remembering those. The segment QR that is inside of our circle is called a chord. Segment QR is a chord. A chord connects 2 points, in this case Q and R, on a circle. And we also learned that if this was a line that intersects with our circle in 2 places, we would have called it a secant. Now, it's not a line, it's a segment, and therefore we call PR a secant segment. Similarly, we learned that if a line touches a circle in just 1 point, that's a tangent. And if it's not a line that touches that point in one segment, it is I can hear you guys say it, a tangent segment. And then we have another segment left here, and that's the segment from P to Q, and that is outside of the circle. And the segment that's outside of the circle is called an external segment. With that being said, let's talk about how we find the length of segments in a circle. And first we're going to start with 2 chords intersecting. In this picture we have 2 chords A, B, and C that are intersecting, and they are intersecting at point E, and that is a very important point, so let's keep that in mind going forward. And by intersecting there, they form 4 segments. On the one hand, they create segment AE and BE, and on the other hand, they create the segments CE and DE. And these 4 segments are proportional to each other in the following way. AE times BE is equal to CE times DE. Now this formula is very important, so let's circle it, put a star on it, and highlight it, and most of all, memorize and remember it. Now you may think that formula is kind of random. Why is that really the case? So let me show you, and you can follow this next proof and copy it maybe on a separate piece of paper, or just lean back, watch, and enjoy. Looking at our 2 intersecting chords, we can add 2 chords to them and make that 2 triangles. And these 2 triangles are connected here by these 2 intersecting lines, forming 2 vertical angles. Angle BED is congruent to angle CEA. And if we keep looking, we have inscribed angle C over here, and if we remember how this inscribed angle forms an intercepted arc here, and look at angle E that also forms an intercepted arc, which happens to be the same arc, that tells us that angle C, or more specifically ACE, has to be congruent to angle ABD. And there you have it. We have 2 pairs of congruent angles, and therefore we can say by AA we do have similar triangles. We have two similar triangles, and in similar triangles, the side lengths are proportional to each other. Remember? So we can set up a statement of proportionality, saying, starting with the shortest side length, side CE is proportional to side BE, the shortest side of the other triangle, and that has to be equal to the side AE over the side DE. Here's a proportion, and how do we solve proportions? We cross multiply. So let's do that. We get AE times BE is equal to CE times DE. Does that look familiar in any way? It should, because that's the formula you just wrote down. Here it is. So memorize this formula. You will need it for all types of problems that we have in this lesson. And remember specifically one thing. Each of these segments end in point E. So E is in each one of these segment names. Let's go and practice this with some examples. Find the value of x. And in example 1, we have segment AE, which is x, times segment BE, which is 4, and that's equal to segment CE, which is 3, times segment DE, and that's 8. So 4x is equal to 24. Divide both sides by 4, and x is equal to 6. Let's go to example 2. Here, the chords are not named with letters, but that shouldn't bother us too much. We got a segment x and another segment x, so x times x. So here be careful not to write 2x because we're not adding these. For this type of exercise, we're multiplying the lengths of the two chords. X times x is equal to 4 times 9. So x squared is equal to 36. And now we're going to have to take the square root of both sides. Square root of x squared is x, and that is positive or negative the square root of 36. But here we are looking for the length of a chord. And does it make sense for a chord to have a length of a negative number? It doesn't really. So the answer is x is equal to positive 6. We can also find the length of two secant segments intersecting, and when they intersect outside of the circle. That's our intersection point E, and that's the one we have to remember to use in our formula in all chords. And when they intersect on the outside of the circle, and this is our intersection point E. When that happens, they create an external segment EA, and a secant segment, which is EB, and another external segment EC, and also a secant segment ED. So we can write AE times BE is equal to CE times DE, and that is exactly the same formula as before. we can go through the proof of why that is the case, but we don't have to do that at this point. What's important is, again, to memorize this formula, realize that it's exactly the same one that we had before, and that those four segments all have an E in their name. AE and CE are the external segments, and BE and DE are the secant segments. Okay, are you ready for some examples? Here we go. Find the value of x. So we have segment AE that has a length of 4 units. And then we have segment BE, the secant segment. And for that, we have to add these two side lengths. Don't take the 6. It's 6 plus 4, so that is 10. So 4 times 10 is equal to, and then we have the other two. Our external segment CE is 5 units long, and our secant segment DE is x plus 5 units long, so times x plus 5. 40 is equal to 5x plus 25 after we have distributed our 5. Subtract 25 from both sides. 15 is equal to 5x, and now we divide by 5, and 3 is equal to x. Now go ahead and stop the video and do the next one yourself, and then come back and check your work with my answers. Stop the video, I said. Hopefully you came up with the same answer. We got external segment 3 times secant segment 9 on the one hand, and we got external segment x times secant segment 2x. So here we had to add the 2x's, but then going forward we multiply them. We get 27 is equal to 2x squared. Divide by 2 to get rid of your coefficient. Then take the square root of both sides. Keep the fraction, at least that's what I did. So then x is equal to the square root of 27 halves. If you went ahead and rationalized the denominator, good for you. That would be square root of 54 divided by 2. Or you use the calculator and you get approximately 3.7. Alright, so much for this, and now go ahead and watch the second part of this tutorial.